Hello, welcome to another module in this massive open online course. So, we are looking at convex optimization, various problems and their applications. Let us start looking in this module at a different class of problems, and which is very interesting and at the same time very powerful, and also understand the various applications. This is known as semi-definite programming. All right. So, it is a slightly more advanced and, as I said, a very useful class of process. So, this is known as semi-definite program. Simply termed as an SDP for semi-definite program. Okay. And as I said, this is a very important and powerful, very interesting as well as, and very important and powerful class of problems. And what is a semi-definite program? Put simply, a semi-definite program is the following, where you are minimizing a seemingly simple objective, that is, objective is still a linear objective. So, you have a linear objective okay. However, the constraint is something interesting. The constraints are, well, first let me write the equality constraint, that is A x bar equals B bar. Again, this is something that is very similar, but the inequality constraint is something very interesting. You have x1 f1 plus x2 f2, that is a linear combination of a weighted combination of matrices xn, or rather an affine combination of matrices xn fn plus g. These are matrices, this is less than or equal to 0, okay. Or you can also say this is greater than or equal to 0. So, you have x1 f1 plus x2 f2 xn fn so on. So, what is this? This is a weighted combination, okay, a linear or affine combination . That is, you are combining these matrices f1 f2 fn comma j. So, these are matrices, okay. Okay, these are matrices, and what you are doing is you are performing a weighted combination, a linearly weighted combination of these matrices, okay. You are performing a linearly weighted a linearly weighted combination of these. You are performing a linearly weighted combination of these matrices, and at the same time, okay. So, you are performing a linearly weighted combination of these matrices, and also if you look at this inequality here, this is a generalized inequality. You can see what this means. Now, this is very interesting because what we have on the left is a matrix, okay. we are saying this matrix has to be greater than or equal to 0, which implies that this matrix has to be positive semi definite. So, this quantity, this inequality for a matrix where A is a matrix, this implies that A has to be a positive semi definite matrix. Which in itself is interesting, because now we are defining an ordering or an inequality on the set of matrices, which is rather unusual because typically you cannot compare two matrices. So, this inequality, this generalized inequality basically specifies that the matrix A has to be positive semi definite. Okay. So, this optimization problem, the first constraint is an equality constraint, the second inequality constraint is a generalized inequality. What it says is this weighted combination of matrices, this says that this weighted combination of matrices, this weighted combination of matrices has to be positive, this weighted combination of matrices has to be positive semi definite. Okay. So, this has to be positive semi definite, all right. Okay. And in fact, this inequality itself, this generalized inequality on the set of positive semi definite matrices is interesting. Let me just briefly describe this. We say two positive semi definite matrices, that is A is greater than or equal to B, that is where A is a positive semi definite matrix, this is a PSD matrix, and this is also a PSD matrix. We say A is greater than or equal to B if and only if x bar transpose A x bar is greater than or equal to x bar transpose B x bar for all x bar. Okay. So, if any vector x bar transpose A x bar, remember for a positive semi definite matrix x bar transpose A x bar has to be always greater than or equal to 0. So, if x bar transpose A x bar is always greater than or equal to x bar transpose B x bar, then we say that the matrix A is greater than or equal to matrix B. Okay. And note that this also implies that x bar transpose A minus B x bar is greater than or equal to 0. Okay. So, this implies that A minus B is positive semi definite. So, A greater than or equal to B implies that A minus B, in fact you can put this as implied is implied by A minus B is positive semi definite. This is another way of defining the same thing. Okay. So, A minus B is positive semi definite. Now, similarly for positive, if you have a strict inequality A greater than P, naturally this implies x bar transpose A minus B x bar is greater than 0 for all x bar. This implies A minus B is positive definite. With this implies A minus B is positive definite. All right. So, A is strictly greater than B if A minus B is positive definite, A is greater than or equal to B if A minus B is positive semi definite. This is the notion of this generalized inequality on the set of positive semi definite matrices. Okay. Now, let us look at an interesting application for this semi definite programming. This has, as I said, it is very interesting, it is powerful, it has several applications. So, let us look at an application of SDP and the application is as follows. Again, let us go to our MIMO wireless system. So, let us consider a MIMO system, and we want to perform MIMO symbol decoding. As we know, as you well know by this point of time, that MIMO stands for multiple input. This is something that you are all very familiar with, multiple output communication system, all right, which is very popular in the context of wireless to achieve high data rates. Okay. And what do you mean by multiple inputs? Multiple inputs means multiple transmit antennas, multiple output means the multiple receive antennas. So, in this MIMO system you have multiple TX antennas and you have also multiple RX equals R, and I can represent this MIMO system model as y bar equals h x bar plus n bar, where you have this vector of received symbols y1, y2, yr equals h times x1, x2, xt, these are t transmitted symbols, plus n bar, which is an r cross 1 vector. Okay. Now, remember you have r output symbols on the r antennas, and you have t transmit symbols. On the T transmit antennas. Now, the point is each of these symbols, right, if you look at each xi in a digital communication system, each symbol xi has to be drawn from a constellation, that is, it cannot take any possible value. For instance, if it is BPSK, it has to be plus or minus 1, if it is QPSK, it is plus or minus 1 plus or minus j, that is, you can have only 4 possible symbols, 1 plus j, 1 minus j, minus 1 minus j, minus 1 plus j. Okay. So, each xi is you have to draw it is drawn from a suitable digital constellation for a digital wireless system. Example BPSK. This is basically your binary phase shift keying, okay, which implies there are two phases. As you are seeing, this is a binary phase shift keying. This implies each xi belongs to plus or minus 1, okay, so which means each xi can be plus or minus 1. Now, that means each xi has two possible values, okay, so each xi can be plus or minus 1. That means each xi has two possible values, implies if you look at the symbol vector x bar, which has x1, x2, x2 up to xt. So, if you look at x bar, which has x1, x2, xt, each has two possible values, implies x bar 2 times 2 times so on up to 2, which is 2 to the possible t transmit vectors for BPSK. Alright, so basically now you observe something interesting. The size of this set, the set of the vector constellation, like corresponding to each digital constellation, right, of xi, which is for instance belongs to BPSK, you have a corresponding vector constellation where to which these vectors x bar belong, and that is of the size 2 raised to the power of t, which is growing exponentially in the number of transmit antennas t. That is the problem. So, this size of the vector constellation number of in the number of in the number of transmit antennas t, all right, and therefore what is the problem? So, this is growing exponentially, okay. Now, what is the problem? So, where is the problem? The problem is, okay, so now let us say we have the set S equal to set of all possible transmit vectors or possible digital transmit vectors. Set of all possible digital transmit vectors x bar, and now this set has 2 to the power of t elements, okay, and therefore now what is the problem? The problem is at the receiver, once you receive y, correct, we have to find the x bar that has been transmitted, the vector x bar that has been transmitted, okay, at receiver. Given y bar, we have to find x bar, that is, or estimate or estimate is not a good word, let us say we have to decode x bar, find x bar, or let us say one has to decode, okay. So, therefore, now the typical decoder that you use, or the best possible decoder, is what is known as the ML decoder, that is, you look at this error y minus h x bar, this is the error, you look at the norm and the norm square of the error, and you minimize the norm square of the error, you find the vector x bar which minimizes the norm square of the error, that is known as argument, okay, or you find the vector x bar which minimizes the norm square of the error. But the problem is, now this x bar must belong to this one of this possible 2 raised to the power of t vectors, that is, this x bar must belong to this set S, or which denotes the transmit vector constellation. So, you have to minimize this with x bar belonging to S. And now we can see the problem is you have to search over all t possible vectors. Search over 2 to the power of t possible vectors, that is the problem, okay. To find x hat, okay, which basically minimizes this, alright. Now, this decoder, this has a name, this is known as the maximum likelihood decoder, which yields the best performance. Okay. Now, you want to apply the maximum likelihood decoder, but you have to perform a search over 2 raised to the power of t vectors, which is increasingly complex as t increases. Okay. For example, if t equal to 10, then 2 raised to the power of t equals 2 raised to the power of 2 equals 1024. So, implies that you have to search for over a set of 1024 possible transmit symbol vectors for each received vector y. So, you have to search over possible tx vectors to decode each vector y. To decode each vector y. And further this observe that this increases with the constellation. For instance, if you have 16 QAM, then the number of vectors becomes 16 to the power of 16 raised to the power of 10, right, for example, and this increases with the number of vectors. Example, this increases with the size of constellation size. Example, for 16 QAM, and this becomes a size of S, that is a transmit vector constellation equals 16 power t. Now, t equal to 10 implies you have 16 to the power of 10 vectors in H over which you have to search, and this is impossible, implies the search is impossible. Or next to impossible, implies the search is impossible. Okay. And therefore, we have to come up with low complexity. Therefore, what we have to do, we have to come up with, hence we need to come up with low complexity techniques, hence we need and one such technique is basically your what is termed as SDP relaxation. We have seen what is SDP already. SDP is semi definite program. So, one such technique is SDP relaxation. We relax this ML decoder problem as a semi definite program. Okay. So, we can formulate this problem as a semi, which we are going to see subsequently shortly, alright. We are going to formulate this ML decoder as a semi definite program, which has a significantly lower complexity, and that is the important thing. This has a alright. So, this is the SDP relaxation for ML decoding, or for I would say rather MIMO ML. This is for the MIMO ML decoder, which has a significantly lower complexity, and this is a very interesting. So, therefore, this is very useful for practical implementation, right. So, this is a significantly lower complexity in comparison to the full ML decoder, the optimal ML decoder, which has exponential complexity, alright, which is virtually impossible for a large number of transmit antennas and large constellation sizes. So, we perform an SDP, we formulate this as an SDP, semi definite program, which can be solved very efficiently, alright, using modern convex solvers, and therefore, the resulting ML decoder, or what we can say that it is an approximate ML decoder, has a significantly lower complexity, alright. So, we will stop here, and this SDP relaxation, and how is SDP exactly used for ML decoding, what is the procedure for that, we will look at it in the subsequent module. Thank you very much.